Somewhere in the constellation Cygnus, about 245 light-years from Earth, a planet watches two suns rise instead of one. A pale orange sun rises over an alien horizon alongside its smaller red companion. The two stars climb together through an unfamiliar sky, casting double shadows across cloud tops that have never known a single source of light. On this world, shadows fall in pairs, and the light never comes from a single direction. This is a world where sunrise means two suns rising, where noon means two suns overhead, and where sunset paints the sky in colors no human eye has ever witnessed directly. This is Kepler-16b, the planet with two sunsets. You're watching The Drowsy Astronaut, where tonight we travel to one of the most remarkable worlds ever discovered beyond our solar system. This is a journey designed for slow listening, for resting, for letting fascinating facts carry you gently towards sleep, or simply keeping you company through the quiet hours. If you'd like to share where you're listening from tonight, the comments are always open, and if these videos help you unwind, a like or subscribe genuinely supports what we do here. Now, let us drift toward a sky that holds two suns instead of one. The idea of a planet orbiting two stars was once considered the stuff of pure science fiction, a fantasy made famous by distant desert worlds in movies and novels. Astronomers debated for decades whether such worlds could actually exist, whether the complex gravitational interactions of a binary star system would tear any forming planet apart. The mathematics seemed to suggest that stable orbits might be possible, but theories required confirmation that only observation could provide. Then, in 2011, the Kepler Space Telescope found Kepler-16b, and the debate ended forever with a single, remarkable discovery: orbiting two stars. This cold gas giant, roughly the size of Saturn, traces a patient path around not one, but two suns locked in their own gravitational embrace. The science fiction had become science fact, proven by the steady dimming of starlight as the planet crossed in front of first one star, then the other. The system lies in the direction of the constellation Cygnus the Swan, a region of sky rich with stars, and the target of Kepler's original planet-hunting mission. From Earth, the two stars appear as a single point of light, their separation far too small to resolve without specialized instruments. But the light curve, the pattern of brightness changes over time, revealed the truth of what was happening out there in the cosmic distance. The two suns of this system are not identical twins, but rather an unequal pair, one notably larger and brighter than its smaller, dimmer companion in perpetual orbit together. The primary star, known as Kepler-16a, is a K-type orange dwarf, cooler and smaller than our own sun, but still substantial enough to dominate the system. It glows with an orange-yellow light, somewhat warmer in hue than our sun's yellow-white, providing most of the illumination that reaches the planet. The secondary star, Kepler-16b, is a red dwarf, significantly smaller and cooler than its companion, contributing a deeper reddish light to the mix. Red dwarfs are the most common type of star in our galaxy, but they are so dim that none are visible to the naked eye from Earth, despite their abundance. This small red sun adds its own distinct color to the light that falls upon Kepler-16b, creating a blended illumination unlike anything in our solar system. These two stars orbit each other every 41 Earth days, locked in a dance that has continued for billions of years since the system first formed from a cloud of gas and dust. They circle their common center of mass, a point in space located between them but closer to the larger primary star due to its greater mass. From the planet's perspective, this means the two suns are constantly moving relative to each other, sometimes appearing close together in the sky and sometimes separated by a wider angle. Imagine, if you can, standing on a hypothetical moon orbiting this gas giant, looking up at a sky that defies everything your Earth-trained instincts expect to see overhead. Two distinct disks hang in the heavens, one larger and orange, the other smaller and notably redder, both providing their own shadows and their own warmth. The orange sun appears perhaps 2/3 the size that our sun appears from Earth, while the red companion looks smaller still, perhaps half that apparent diameter. The light that falls upon you is not the pure yellow-white of Earth's sunny days, but something altogether different, a blend of orange and red wavelengths that would make colours appear shifted and strange. Objects that appear blue on Earth might look different under this alien illumination, while reds and oranges might seem more vivid and pronounced than we are accustomed to seeing. The entire colour palette of this world would be subtly transformed by the nature of its double light source. Shadows on this world come in pairs, each object casting two distinct darkened areas that point in slightly different directions depending on where each sun hangs in the sky. When the suns are close together in their apparent positions, these double shadows nearly overlap, creating a single darker umbra with lighter penumbral edges fading outward. When the suns are separated by a wider angle, the shadows pull apart, each one distinct, each one a different shade, depending on which sun it blocks. The experience of a day on Kepler-16b, or rather, on a moon orbiting this gas giant, would be unlike any day on Earth in ways both subtle and profound. Morning would bring not one sunrise, but potentially two, the suns appearing over the horizon either together or separately, depending on their orbital positions relative to each other. Sometimes the orange sun would rise first, flooding the landscape with its warmer light before the red companion followed minutes or hours later. Other times, the two suns might rise almost simultaneously, their disks appearing side by side as they climb above the horizon in a display of celestial companionship. The light would intensify as both sources clear the horizon, filling the sky with a brightness that increases in stages rather than all at once, as we experience on Earth. Noon would bring both suns to their highest points, though not necessarily at the same altitude, their combined light at its maximum intensity. The afternoon would see the suns descending, again either together or in sequence, their light gradually shifting as the angles change and the atmosphere scatters different wavelengths. And then would come sunset, or rather, sunsets, the phenomenon that gives this episode its name, the double setting of two suns below an alien horizon. This is what we came here to experience, and we will explore it deeply in the passages that follow. The planet itself is a gas giant, a world without solid ground, composed primarily of hydrogen and helium, like our own Jupiter and Saturn. Kepler-16b is roughly similar in size to Saturn, perhaps slightly smaller, with a mass about 1/3 that of Jupiter, making it a substantial world by any measure. If you could somehow descend through its atmosphere, you would find no surface to land upon, just increasingly dense layers of gas, transitioning eventually into liquid and perhaps exotic forms of matter under extreme pressure. This means that the experience of double sunsets we imagine is not something that could occur on the planet itself, at least not in any way a human observer could witness directly. Instead, we must imagine standing on a hypothetical moon, a rocky or icy satellite orbiting this gas giant, sharing its view of the two suns above. Such moons are common around gas giants in our solar system. Jupiter has dozens, Saturn even more, and Kepler-16b likely possesses its own collection of natural satellites. From such a moon, the view would be extraordinary, with the banded atmosphere of the gas giant dominating one portion of the sky, while the two suns commanded attention from another quarter. The planet would loom large, reflecting the orange and red light of its twin suns, its cloud bands painted in colors we can only guess at from our distant vantage here on Earth. This is the viewpoint we will adopt as we continue our exploration of this remarkable system. The orbital path of Kepler-16b carries it around both stars together, not around one, while the other circles separately at a greater distance. This type of orbit is called circumbinary, meaning the planet circles the binary pair as if they were a single gravitational source located at their combined center of mass. The planet takes approximately 229 Earth days to complete one orbit, its year lasting a little less than 8 Earth months. This orbital period places Kepler-16b at a distance from its suns roughly equivalent to Venus's distance from our sun, about 3/4 of an astronomical unit. However, because both suns are dimmer than our sun, the planet receives less total energy than Venus does, resulting in temperatures far colder than that scorched world experiences. Estimates suggest the planet's effective temperature is around -70 to -100 degrees Celsius, making it a frozen world despite its proximity. The orbit itself is remarkably circular, with very little eccentricity, meaning the planet maintains a relatively constant distance from the center of mass of the two stars throughout its year. This stability is somewhat surprising given the complex gravitational environment, but it suggests the system has settled into a long-term stable configuration over billions of years. The planet has survived in this configuration, and it will likely continue to survive for billions of years more. The cold temperatures on Kepler-16b mean that this is not a world where liquid water could exist on any hypothetical surface, at least not in exposed form under normal conditions. Any moons orbiting this gas giant would likely be frozen, their surfaces covered in ice composed of water, ammonia, methane, or other volatile compounds. The double sunlight falling upon these icy surfaces would create glittering reflections, each sun producing its own highlights and sparkles. Yet cold does not mean dead in the cosmic sense, and frozen moons can still be geologically active if internal heat from tidal forces keeps their interiors warm despite frigid surfaces. In our own solar system, moons like Europa and Enceladus maintain liquid water oceans beneath their icy crusts, heated by the gravitational flexing caused by their giant planet hosts. If similar moons orbit Kepler-16b, they too might harbour subsurface oceans warmed by tidal heating. We cannot know for certain whether such moons exist, as our current instruments cannot detect the small satellites that might orbit a planet 245 light-years away. But the possibility is intriguing, adding another layer of wonder to an already remarkable system that has captured the imagination of astronomers and public alike since its discovery. Perhaps, beneath the ice of some unnamed moon, liquid water exists. The discovery of Kepler-16b represented a turning point in our understanding of where planets can exist and how diverse planetary systems can truly be. Before this confirmation, circumbinary planets remained theoretical possibilities, predicted by mathematics, but never observed directly in the real universe around us. The detection changed everything, proving that nature had found ways to form stable worlds, even in the complex gravitational environments of binary star systems. The Kepler mission went on to discover additional circumbinary planets after this initial breakthrough, each one adding to our catalogue of worlds with 2 suns in their skies. Some of these systems are quite different from Kepler-16, with different stellar types, different planetary sizes, and different orbital configurations that create their own unique experiences. The category of circumbinary planets, once empty, now contains over a dozen confirmed members, with likely many more awaiting discovery. But Kepler-16b remains special as the first, the world that proved such planets were possible and opened our eyes to the diversity of the cosmos. It occupies a unique place in the history of exoplanet science, a landmark discovery that expanded the boundaries of what we knew to be real. Whenever future generations look back on the early days of planet hunting, this world with its 2 suns will be remembered as a pioneer. The view from Kepler-16b's vicinity is something we can simulate with computers and imagine with our minds. But no human eye has ever seen it directly. The 245 light-years separating this system from Earth represent an unbridgeable gulf with current technology, a distance so vast that even light takes nearly 2.5 centuries to cross it. We observe this world from afar, reading its secrets from the subtle variations in starlight that reach our telescopes. Yet there is something beautiful about this remote observation, this ability to know something about a world we can never visit through any means currently available to us. The double sunsets of Kepler-16b occur whether we watch them or not, the 2 suns setting below alien horizons every few hours as hypothetical moons rotate beneath them. Our knowledge does not change what happens there, but it enriches our understanding of what the universe contains. Tonight, as you listen to these words, those 2 suns are there in the constellation Cygnus, shining their blended orange and red light upon a cold gas giant that orbits them both. The system continues its operations as it has for billions of years, stars orbiting each other, planet orbiting stars, moons perhaps orbiting planet, all of it proceeding according to the laws of gravity and motion. It is a clockwork of cosmic proportions, patient and precise. In the next part of our journey, we will explore more deeply what the sunsets themselves would actually look like on this remarkable world with its 2 distinct suns. We will consider the colors, the sequences, the moments when one sun sets while the other still hangs above the horizon, and the rare occasions when both descend together in a display of celestial beauty that exists nowhere in our solar system. The sunset on Earth is a singular event, our one sun descending below the western horizon, while the sky transitions through familiar gradients of orange, pink, and purple before darkness claims the landscape. We know this experience intimately, have watched it countless times throughout our lives, have taken for granted the simplicity of a single source of light departing from a single direction. It is beautiful, yes, but it is also the only version of sunset we have ever known. On Kepler-16b, or on a moon orbiting this distant gas giant, the experience of sunset would be something fundamentally different, a doubling of the phenomenon that adds complexity and strangeness. Two suns mean two sunsets, and those two events can occur simultaneously, separately, or in partial overlap, depending on the geometry of the moment you happen to witness them. Each configuration creates its own unique display of light and color. The simplest case to imagine is when both suns set at roughly the same time, their disks descending toward the horizon in close proximity to each other. In this scenario, the sky would blaze with a concentrated intensity of orange and red light. As both sources approach the horizon simultaneously, their combined colors blending together. The horizon itself might glow with an almost molten appearance, light from two distinct sources merging into a single band of warmth. As the suns touch the horizon in this simultaneous scenario, the larger orange primary would appear to flatten first, its lower edge distorted by atmospheric refraction, just as our sun appears to flatten at sunset on Earth. The smaller red companion, still slightly above, would cast the longer shadows now, becoming briefly the dominant light source in those final moments before it too begins its descent. The transition would create a subtle but noticeable shift in the color of everything, from the blended orange-red to a purer red tone. When both disks have slipped below the horizon, the afterglow would be extraordinary, a twilight unlike any on Earth, painted in hues that our single sun cannot produce alone. The upper atmosphere would scatter the last rays from both departed suns, creating layers of color that might persist for longer than our familiar twilights, simply because there is more light to scatter. Darkness would come eventually, but it would arrive more gradually, more gently than the sharper transition we experience with our solitary star. The stars would emerge slowly into this extended twilight, first the brightest ones becoming visible against the still glowing sky, then gradually more as the darkness deepened and the sun glow faded. The gas giant planet itself, if visible from our hypothetical moon, might continue to glow with reflected sunlight even after both suns had set from the moon's perspective, its massive globe catching rays that still reached it from its higher vantage point. But the two suns of Kepler-16 do not always set together, and the more common experience would be sequential sunsets, one sun descending first while the other remains above the horizon for some additional time. Imagine watching the smaller red sun dip below the horizon while the larger orange primary still hangs midway up the sky, still flooding the landscape with its warmer, brighter light. The shadows would shift from double to single, and the color palette would change from blended to purer orange. In this scenario, the departure of the red sun would be almost subtle, a diminishment of the red component in the overall illumination, rather than a dramatic plunge into darkness. You might notice the shadows becoming sharper, losing their softer reddish edges, as only the orange sun remained to cast them with its single source of light. The temperature might drop slightly as one source of warmth departed, though on such a cold world, this change would be minimal. Then, hours later perhaps, the orange sun would make its own descent, and this sunset would be the more dramatic of the two, the primary source of light finally taking its leave. The sky would transition through deeper oranges than Earth ever sees, the cooler stellar temperature creating a sunset palette weighted toward the warmer end of the spectrum. When this sun finally slipped away, the darkness would be more complete, both sources now gone. The opposite sequence is equally possible, with the larger orange sun setting first, while the smaller red companion lingers in the sky alone. This configuration would create a particularly eerie and beautiful experience. the landscape suddenly bathed in pure red light, without the balancing orange of the primary star. Everything would take on a ruddy, almost ominous appearance, shadows stretching long and dark, with only the dim red sun to provide illumination. This red twilight period might feel strange to human eyes, accustomed as we are to red light signaling the end of day rather than constituting the primary illumination. The overall brightness would be lower than before the orange sun's departure, perhaps comparable to early twilight on Earth. Enough to see by, but not truly bright. Colors would be distorted, blue and green objects appearing grey or brown under light that lacks those wavelengths. When the red sun finally set as well, completing the second sunset, the darkness would arrive as a culmination of a longer, more gradual process than Earth's single sunset provides. The extended twilight under red illumination would give way to night, the stars emerging in their full glory above a world that had just experienced something no human has ever witnessed. Directly, two sunsets, each distinct, each beautiful, separated by an interval of strange red daylight. Perhaps the most spectacular events in the sky of this system would be the eclipses, the moments when one star passes in front of the other, as seen from the planet's location in space. These stellar eclipses happen regularly, given the 41-day orbital period of the two stars around each other, and they would be visible from anywhere in the system with a clear line of sight. The effect on illumination would be dramatic and immediate. When the smaller red sun passes in front of the larger orange primary, it blocks a portion of the orange light, creating a partial eclipse that dims the overall brightness significantly. From the planet or its moons, you would see a dark disk moving across the face of the brighter sun, the red star appearing as a silhouette against its companion. The shadows would shift and change as the eclipse progressed, the light becoming redder as more of the orange source was blocked. At maximum eclipse, if the red star passed directly across the center of the orange disk, the light would be substantially diminished, perhaps by 30 or 40%, depending on the exact alignment. The color of the illumination would shift strongly toward red, the only direct light coming from the unblocked portions of the orange sun around the edges of the eclipsing red star. This would create a surreal midday twilight, darkness in the midst of what should be full daylight. The opposite type of eclipse, when the larger orange star passes in front of the smaller red companion, would be a different experience entirely, more subtle, but still noticeable. The red sun would disappear behind the brighter orange disk, and for a time, all illumination would come from a single source, the orange primary alone. This might feel almost normal to Earth-trained eyes, a temporary return to the single sun experience we know. The shadows during this type of eclipse would be crisp and singular, cast by only one light source rather than the usual blurred double shadows created by two suns. The color palette would be simpler as well, pure orange-yellow, without the added red component that usually mingles with it in this system. When the red sun emerged from behind its companion, the double shadows would return, and the subtle red tint would creep back into the illumination. These eclipses would become familiar events to anyone living in this system, regular occurrences that punctuate the cycles of day and night with their own rhythm. They would be predictable, following the 41-day orbital period of the stellar pair, allowing inhabitants to anticipate when the sky would dim and the light would shift. The strangeness would become normal, the extraordinary becoming routine through repetition over years and generations. The atmosphere through which these sunsets and eclipses are viewed would play its own role in shaping the experience. Just as Earth's atmosphere shapes our perception of our single sun, we do not know the exact composition of any atmosphere that might exist on a moon of Kepler-16b. but we can imagine possibilities based on moons in our own solar system. A thin nitrogen atmosphere, like Titan's, would scatter light differently than Earth's oxygen-nitrogen mix. A thicker atmosphere would create more vivid sunsets, with more scattering of shorter wavelengths and more enhancement of the already warm colors of these two cool stars. The suns might appear to flatten more dramatically near the horizon, their shapes distorted by refraction as they shone through greater thicknesses of atmospheric gas. Hazes or clouds in the atmosphere would add their own colors, perhaps creating layered sunsets of unusual complexity and beauty. Even a world with no atmosphere at all, a bare rocky moon exposed directly to space, would experience the double sunsets, though without the atmospheric effects that make Earth's sunsets so colorful. The suns would appear as sharp disks against the black sky, setting behind rocky horizons with geometric precision, their departure marked by sudden transitions from light to shadow. Beauty takes different forms under different conditions. The gas giant itself, Kepler-16b, would be a constant presence in the sky of any close-orbiting moon, a vast globe that waxes and wanes through phases like our moon does from Earth. But this planetary companion would be enormous compared to our moon, filling a substantial portion of the sky, depending on the moon's orbital distance from its parent world. Its cloud bands would be visible, painted in colors determined by the double sunlight illuminating them. As the two suns set from the moon's perspective, the gas giant might still catch their light, glowing with reflected orange and red radiance against the darkening sky. This planetary glow could provide substantial illumination even after both suns had set locally, a kind of extended twilight caused by light bouncing off the giant planet's cloud tops. The night would never be completely dark as long as the planet reflected any sunlight toward its moon. The interplay between the two suns, the gas giant, and any moons creates a system of extraordinary visual complexity that changes constantly throughout the orbital periods involved. No two sunsets would be exactly alike. No 2 days would have precisely the same sequence of illumination events. No 2 nights would be lit in identical ways. The variety would be endless, the beauty ever renewing. We speak of these experiences in concrete terms, but we must acknowledge that no human has ever seen them, and likely no human ever will, at least not directly with unaided eyes. The distance is too great, the journey impossible. With any technology we currently possess or can reasonably envision for centuries to come, Kepler-16b remains forever out of reach, its double sunsets occurring unseen by any witness we can confirm. Yet there is something valuable in imagining these unreachable experiences, in using our minds to visit places our bodies cannot go and will never touch. The imagination has no speed limit, no fuel requirement, no life support needs that must be met for the journey. We can drift toward Kepler-16b in thought, stand on hypothetical moons, and watch 2 suns set simply by closing our eyes and constructing the scene from what science tells us must be true. The double sunsets are real, even if no one watches them, even if no consciousness in that system has ever evolved to appreciate them. The suns set because physics demands it, because the rotation of moons creates horizons, because light travels in straight lines that eventually curve below rocky surfaces as celestial bodies turn. Reality does not require observation to proceed. The colors of these sunsets exist on a spectrum that our eyes could perceive if we were there. Wavelengths of light that fall within the range human vision can detect and interpret. Orange light around 590 to 620 nanometers. red light from 620 to 700 nanometers. These are the hues that would dominate the sky of Kepler-16's moons at sunset. Our eyes are built to see such colors, even if they are painted by unfamiliar suns. There is something comforting in this shared physics, this common chemistry of light and vision that would make an alien sunset at least partially comprehensible to human observers. We might not recognize the landscape or understand the context, but we would know we were watching a sunset, would feel the ancient pull of day ending that our species has felt for hundreds of thousands of years. The experience would be alien and familiar simultaneously. Perhaps this is why the image of a planet with two sunsets captures our imagination so effectively, bridging the gap between the utterly strange and the deeply known. We have all watched sunsets, have all felt the particular peace that comes with the day's end, and imagining that experience doubled allows us to project ourselves into the scene. We can almost feel what it might be like, almost see what we have never actually seen. As we continue deeper into the story of Kepler-16b, we will explore the stars themselves more thoroughly, understanding what kinds of suns they are and how they differ from our own. We will examine the planet in greater detail, considering its size, composition, and the conditions that prevail in its frozen atmosphere. The two suns of the Kepler-16 system are both smaller and cooler than our own sun, representing types of stars that are actually far more common in the galaxy than yellow stars like the one that warms our Earth. If you could somehow replace our sun with either of these stars, our planet would freeze, too far from the reduced warmth to maintain the liquid water that makes our world habitable. Yet these cooler stars have their own kind of beauty, their own long lives ahead of them. Kepler-16a, the larger and brighter of the pair, belongs to a class of stars known as K-type dwarfs, sometimes called orange dwarfs due to their characteristic color. These stars range from about half to 3/4 the mass of our sun, and they burn their hydrogen fuel more slowly, giving them lifespans that can exceed 20 billion years. Our sun, by comparison, will exhaust its hydrogen in about 10 billion years total, half of which have already passed. The color of Kepler-16a is distinctly orange, warmer in hue than our yellow sun, but not as red as the smaller companion that shares its system. The surface temperature is approximately 4,500 Kelvin, compared to our sun's 5,800 Kelvin, the difference clearly visible in the shifted spectrum of light it emits. If you could stand beneath this star, the daylight would feel different, warmer in color, if not in physical warmth. Kepler-16b, the smaller companion, is a red dwarf, the most common type of star in our galaxy, and yet entirely invisible to the naked eye from Earth due to their extreme dimness. Red dwarfs can have as little as 8% of our sun's mass, barely enough to sustain hydrogen fusion in their cores, and they burn so slowly that they can shine for trillions of years. When our sun has long since died and cooled to a black cinder, red dwarfs, like Kepler-16b, will still be shining. This small red star has a surface temperature of only about 3,500 Kelvin, giving it its characteristic deep red color that would be immediately apparent to any observer. Its light is weighted heavily toward the red and infrared portions of the spectrum, providing warmth that eyes cannot see alongside the dim visible glow that they can. Plants evolved under such a star might be black rather than green, absorbing all available wavelengths rather than reflecting any back. The radius of Kepler-16b is only about 1/3 that of our sun, making it a truly compact stellar furnace compared to the bloated giants that capture most of our attention in popular astronomy. If you placed this star where our sun is now, it would appear as a small reddish disk in the sky, providing far less light and warmth than we currently enjoy. Earth would freeze solid within months under such diminished illumination. The two stars orbit each other with a period of 41 days, circling their common center of mass in paths that bring them alternately closer and farther from that central point. The separation between them varies as they orbit, ranging from roughly 20 to 40 million kilometers depending on their orbital phase. At closest approach, they are about half the distance from Mercury to our Sun, while at farthest, they are comparable to Mercury's orbital distance. This orbital dance has continued for billions of years and will continue for billions more. The two stars locked in mutual gravitational embrace since they formed together from the same cloud of gas and dust. Binary star systems like this one are actually quite common in the galaxy, with perhaps half of all Sun-like stars having at least one stellar companion. Our own solitary Sun is somewhat unusual in its isolation. From the planet's perspective, the two stars would appear to move around each other in a complex pattern that repeats every 41 days, but changes somewhat throughout the planet's own 229-day orbit. Sometimes the stars would appear close together in the sky, nearly overlapping from the planet's viewpoint. Other times they would appear separated by a wider angle, casting shadows in noticeably different directions. The combined luminosity of both stars is only about 1/4 that of our Sun, meaning the Kepler-16 system produces far less total light than we receive here on Earth. This reduced brightness, combined with the planet's distance of about 3/4 of an astronomical unit, results in the cold temperatures that characterize this system. Any warmth in this system is precious and scarce. The spectral distribution of the light is also different, weighted more heavily toward longer wavelengths than our Sun's output. More of the energy comes out as red and infrared radiation, less as yellow and blue. A camera white balanced for Earth sunlight would render scenes under Kepler-16's suns with a distinctly orange-red cast. The difference would be immediately apparent. This shifted spectrum would have implications for any hypothetical life in the system, changing the available energy for photosynthesis and altering the chemistry of any atmosphere exposed to the stellar radiation. Ultraviolet light, which drives many chemical reactions in Earth's atmosphere, would be less abundant from these cooler stars. The environment would be different in ways both obvious and subtle. K-type stars like Kepler-16a have attracted considerable attention from astronomers searching for habitable planets, despite, or perhaps because of, their differences from our Sun. Their longer lifespans give more time for life to evolve if conditions are otherwise suitable, potentially tens of billions of years instead of the 10 billion our Sun provides. Any planets in the habitable zone of such a star would have a very long time to develop complexity. The habitable zone around a K-type star is closer in than around our Sun, since the reduced luminosity means planets must orbit nearer to receive sufficient warmth. For Kepler-16a alone, the habitable zone would extend from perhaps 1/4 to half an astronomical unit. But in the Kepler-16 system, the situation is complicated by the presence of two stars and the planet's circumbinary orbit. Red dwarfs like Kepler-16b are even more interesting in some ways, their extreme longevity offering the possibility of life having almost unlimited time to evolve and develop. However, they pose their own challenges, including strong stellar flares that could strip away planetary atmospheres and the tendency for planets in their habitable zones to become tidally locked. This small red star would be a challenging host for life on its own. Together, the two stars create an environment unlike either would produce individually. their combined effects more complex than simple addition would suggest. The planet experiences illumination from two sources moving independently in the sky, each contributing its own color, its own warmth, its own influence on the environment. The result is a world lit by a light that has no equivalent anywhere in our solar system. The gravitational influence of two stars also creates a more complex dynamical environment than a single star would produce. The planet must navigate between competing gravitational pulls, finding an orbit that remains stable despite the changing configuration of its two suns. The fact that such stable orbits exist at all was once doubted by astronomers, but Kepler-16b has demonstrated that nature finds a way, that planets can form and survive in the chaotic-seeming environment of a binary star system. The orbit is not simple, but it is stable. The illumination is not straightforward, but it is consistent enough to allow the system to persist for billions of years. The ages of the two stars are difficult to determine precisely, but estimates suggest the system is several billion years old, likely comparable in age to our own Sun at roughly 4 to 5 billion years. The stars would have formed together from a single collapsing cloud of gas and dust, condensing into two distinct objects that remained gravitationally bound. The planet would have formed somewhat later, coalescing from the disk of material that remained after the stars ignited. This ancient age means the system has had ample time to settle into its current configuration, any unstable arrangements having long since been eliminated by gravitational interactions. The orbits we observe today are the survivors, the configurations that proved stable over timescales of billions of years. What remains is what works. The stars will continue to shine for many billions of years more, the orange primary for perhaps 10 to 15 billion additional years, the red secondary for effectively forever on any timescale meaningful to humanity. Long after our sun has swelled into a red giant and died, Kepler-16's suns will still be there, still circling each other, still illuminating their cold gas giant planet with their double light. The process by which we learned about these stars involved patient observation and careful analysis of the light that reached us across 245 light-years of space. The Kepler Space Telescope watched this system for months, measuring the brightness of the combined starlight with exquisite precision. Every dip, every fluctuation was recorded and analyzed. The stars eclipse each other from our perspective, the smaller red dwarf periodically passing in front of the larger orange primary, and vice versa. These stellar eclipses create distinctive patterns in the brightness measurements, patterns that reveal information about the sizes, temperatures, and orbital parameters of both stars. By analyzing these eclipses, astronomers could determine properties they could never measure directly. The planet's existence was revealed by additional dips in brightness, occurring when the planet itself passed in front of first one star, then the other, during its orbit around the pair. The pattern was complex, with the planet sometimes transiting the orange star, sometimes the red star, sometimes both in sequence. Untangling this complex signal required sophisticated analysis. The names of these stars, Kepler-16a and Kepler-16b, are catalogue designations rather than proper names carrying cultural or historical significance. The system takes its name from the Kepler Space Telescope that discovered it, with the number 16 indicating it was the 16th system of interest in one of Kepler's early target lists. There is no romance in these designations. Yet the stars themselves are as real as any that bear ancient names from mythology and human history, burning their nuclear fuel in cores where temperatures reach millions of degrees. They shine their light across the cosmos regardless of what we call them, whether we name them after gods or assign them database numbers. The lack of a poetic name does not diminish their physical reality. Perhaps future generations will name these stars and their planet with designations that carry more meaning, especially if they become the focus of continued study or capture the public imagination sufficiently. For now, they remain Kepler-16a and b, clinical designations for objects of remarkable beauty. As we continue our exploration of this system, we will turn our attention from the stars to the planet itself, examining what kind of world orbits these two suns and what conditions prevail in its cold, distant realm. The planet has its own story to tell, independent of, but shaped by its remarkable double suns. The planet Kepler-16b is a gas giant, a world without solid ground, composed primarily of hydrogen and helium, with traces of heavier elements mixed throughout its massive atmosphere. In size, it resembles Saturn more than Jupiter, with a radius approximately 75% that of our ringed neighbour, and a mass about 1/3 that of Jupiter. This makes it a substantial world by any measure, yet modest compared to the largest planets we know. The classification as a gas giant means that descending through the atmosphere would never bring you to a surface you could stand upon. The gases simply become denser with depth, transitioning from the near vacuum of the upper atmosphere to pressures that would crush any material we know how to make. Eventually, the hydrogen becomes so compressed that it behaves like a liquid, and deeper still, it may take on metallic properties under extreme pressure. This structure is similar to what we observe in Saturn and Jupiter, worlds we have studied extensively with spacecraft that have orbited them and even plunged into their atmospheres. Kepler-16b is too distant for such direct exploration, but we can infer its general structure from its mass and radius, applying the physics we have learned from our own gas giants to this alien world. The atmosphere of Kepler-16b would be banded with clouds, organized into zones and belts by the planet's rotation and the dynamics of its atmospheric circulation. Jupiter's famous bands are driven by powerful jet streams, and similar features likely exist on any gas giant of comparable size. The colors of these bands would depend on the chemical composition of the clouds at different altitudes. On Jupiter, the colors range from white to orange to brown, created by compounds of sulfur, phosphorus, and other elements mixed into the hydrogen and helium that dominate the atmosphere. Kepler-16b might have similar coloring, or might be different, depending on its exact composition and the unique chemistry driven by its double illumination. We cannot observe these details from Earth. The rotation period of the planet is unknown, as the techniques used to measure rotation require observations we have not yet been able to make at this distance. Gas giants in our solar system typically rotate quickly, with Jupiter completing a rotation in about 10 hours and Saturn in about 11. Kepler-16b likely spins on a similar timescale, its bands of clouds racing around the planet as it turns. The temperature of Kepler-16b is cold by any standard, with an effective temperature estimated at around -70 to -100 degrees Celsius. This is similar to Saturn's temperature, both planets being too far from their suns to receive substantial warming. The clouds in the upper atmosphere would be composed of frozen compounds, ices of ammonia or methane or water. Deep within the atmosphere, temperatures rise due to the pressure of the overlying layers, just as they do in the interiors of Jupiter and Saturn. At some depth, conditions might be warm enough for water to exist as a liquid, though the pressures at such depths would be crushing. The interior of the planet might be surprisingly warm, despite the frigid exterior. The heat in the interior comes partly from the slow contraction of the planet over billions of years, gravitational energy converting to thermal energy as the planet very gradually shrinks. Jupiter radiates more energy than it receives from the Sun, and Kepler-16b might do the same, contributing its own internal warmth to the energy budget of any hypothetical moons. The orbit of Kepler-16b carries it around both stars in a roughly circular path, with a period of 229 Earth days. This circumbinary orbit means the planet circles the center of mass of the stellar pair, rather than either star individually. The path is stable, having persisted for billions of years since the planet formed. The distance from the center of the system varies slightly during the orbit, but the overall configuration keeps the planet in a region where conditions remain relatively constant throughout its year. The two stars provide a combined illumination that doesn't change drastically as the planet moves, the geometry of the system maintaining a rough equilibrium. The stability of this orbit was not guaranteed, and many possible orbital configurations around binary stars are unstable, leading to ejection of the planet or collision with one of the stars. Kepler-16b found or settled into a configuration that works one of the relatively narrow range of stable possibilities. It is fortunate that such stable configurations exist at all. The formation of Kepler-16b remains somewhat mysterious, as the conventional models of planet formation were developed with single stars in mind. In those models, planets form from a disk of gas and dust, orbiting a young star, gradually accumulating material until they reach their final sizes. The presence of two stars complicates this picture considerably. A circumbinary disk would be shaped differently than a disk around a single star, with the inner edge cleared out by the gravitational influence of the stellar pair. Planets forming in such a disk would have to do so farther from the center, in regions where the disk remains stable. Kepler-16b likely formed in such an outer region before potentially migrating to its current location. Alternatively, the planet might have formed around one of the stars individually before being captured into a circumbinary orbit through complex gravitational interactions. This scenario seems less likely given the apparent stability of the current configuration, but it cannot be ruled out entirely. The true formation history may never be known with certainty. The possibility of moons orbiting Kepler-16b is intriguing, as gas giants in our solar system universally possess extensive satellite systems. Jupiter has at least 95 known moons. Saturn has over 140, and even the smaller ice giants Uranus and Neptune have dozens each. It would be surprising if Kepler-16b had no moons at all. These hypothetical moons could range from small, irregular objects captured from passing asteroids to large worlds comparable to Ganymede or Titan, the largest moons in our solar system. Some might have substantial atmospheres. Others might be bare, rocky, or icy surfaces exposed directly to the vacuum of space. The diversity of moons in our solar system suggests the diversity around Kepler-16b could be equally impressive. Any large moons would experience the same double sunsets we have discussed, watching two suns set behind the limb of their giant planet parent or below their own local horizons. They would also experience eclipses by the planet itself, passing through its shadow during each orbit and experiencing sudden darkness as the double sunlight was blocked. The satellite environment would be dynamically complex. The lack of direct observations of Kepler-16b means we must rely on models and inference to understand this world, applying lessons learned from our own solar system to a planet we can observe only indirectly. Every statement about its atmospheric composition, its possible moons, its internal structure, carries uncertainty. We are making educated guesses based on physics and comparison. This limitation is inherent to exoplanet science, where the vast distances involved prevent the kind of close-up investigation we can perform on worlds in our own solar system. Spacecraft have orbited Jupiter and Saturn, have plunged into their atmospheres, have studied their moons up close. No spacecraft will visit Kepler-16b in any foreseeable future. Yet the indirect methods we use are surprisingly powerful, revealing more than might seem possible from light-year distances. We know the mass and radius of the planet, its orbital period and distance, the properties of its host stars. This information constrains what the planet can be, ruling out many possibilities and focusing our imagination on what remains. The name Kepler-16b carries within it the history of its discovery, a reminder that this world was found by a spacecraft designed to hunt for planets around other stars. The Kepler mission was one of the most successful planet-hunting endeavors in history, discovering thousands of planets before its mission ended. This particular planet, the first confirmed circumbinary world, holds a special place among those thousands. The lowercase letter b in the designation indicates that this is a planet rather than a second star in the system. Stars in a binary system are designated with capital letters A and B, while planets receive lowercase letters starting with B. The letter A is skipped to avoid confusion with the primary star. This system of nomenclature is somewhat arcane, but serves the practical purpose of uniquely identifying objects. In the catalogue of known exoplanets, Kepler-16b occupies a unique position as the first of its kind, the planet that proved circumbinary worlds exist. Future discoveries would add to this category, but none would have the same historical significance as the first. This cold gas giant, orbiting its two suns in a distant constellation, changed what we thought was possible. The world continues its orbit tonight, as it has for billions of years, circling its two suns in patient procession, regardless of whether anyone observes it. The cold clouds turn beneath the double light. The possible moons trace their own smaller orbits. The entire system proceeds according to gravitational law. Our knowledge of this world is incomplete, but growing. Now we will explore how this remarkable planet was discovered, the techniques that allowed astronomers to find a world 245 light-years away. The story of discovery is its own kind of journey, one that happened here on Earth in observatories and offices. The year was 2011, and the Kepler Space Telescope had been staring at a patch of sky in the constellation Cygnus for just over 2 years, watching 150,000 stars simultaneously. Its mission was simple in concept, but revolutionary in execution. Watch for the tiny dips in starlight that occur when a planet passes in front of its host star. From this patient watching, a new understanding of the galaxy's planetary population would emerge. The transit method, as this technique is called, requires precise measurements of stellar brightness over extended periods of time. When a planet crosses the face of its star from our perspective, it blocks a small fraction of the starlight, causing a dip in brightness that can be detected with sufficiently sensitive instruments. The depth of the dip reveals the size of the planet, while the timing of repeated dips reveals the orbital period. Kepler was designed to detect these tiny dips, some as small as 0.01% of a star's brightness, the kind of signal that would be lost in noise for any less capable instrument. Its precision made it possible to find Earth-sized planets for the first time, though it would also excel at finding larger worlds in all kinds of configurations. The Kepler-16 system drew attention because its light curve was unusual, showing multiple sets of dips that didn't fit the simple pattern expected from a single star with a single planet. The two stars themselves eclipse each other as they orbit, creating one set of regular brightness variations with a period of 41 days. But additional dips appeared that couldn't be explained by the stellar eclipses alone. Analysis revealed that a third body was present, one that sometimes crossed in front of the orange primary star, sometimes in front of the red secondary, creating a complex pattern of transits that reflected its circumbinary orbit. The depth of these transits indicated an object roughly Saturn-sized, too large to be a brown dwarf or small star. It was a planet, and it was orbiting both stars. The Discovery team, led by Lawrence Doyle of the SETI Institute, announced their findings in September of 2011, publishing in the journal Science with a paper titled simply Kepler-16b, a transiting circumbinary planet. The astronomical community and the broader public took immediate notice. Science fiction had become science fact. The confirmation that circumbinary planets exist resolved a debate that had continued for decades among astronomers and planetary scientists. Mathematical models had suggested that stable orbits around binary stars were possible, but the range of stable configurations was limited, and many had wondered whether real planets could form and survive in such environments. Kepler-16b answered that question definitively. The planet's orbit is remarkably stable, having survived for billions of years in the gravitational environment created by two stars orbiting each other every 41 days. The orbital mechanics work out because the planet orbits far enough from the stellar pair that it experiences their combined gravity rather than being pulled back and forth destructively. At closer distances, the orbit would be chaotic and unstable. This stability requirement means circumbinary planets can only exist in certain orbital ranges, not too close to the stellar pair, where tides would tear them apart or fling them from the system. Kepler-16b orbits at roughly the right distance, far enough to be stable, but close enough to have been detectable by Kepler's transit observations. It occupies a kind of sweet spot. The transit observations that revealed this planet were complex to interpret, requiring sophisticated computer modeling to understand what configuration of stars and planet could produce the observed pattern of brightness changes. Each transit of the planet across one of the stars had to be matched to a model, and the model had to correctly predict when future transits would occur. The agreement between model and observation provided confidence in the result. The team could determine not just that a planet existed, but also its size, its orbital period, and its mass, through careful analysis of how the planet's gravity affected the timing of the stellar eclipses. This timing variation method provided an additional check on the results, confirming the mass of the planet independently of the transit depth measurements. Everything fit together consistently. Additional observations from ground-based telescopes helped confirm the discovery and refine the orbital parameters. The two stars were observed spectroscopically, revealing their individual properties through the characteristic fingerprints of light they emitted. The stellar properties in turn constrained what the planet's environment must be like. The announcement of Kepler-16b generated widespread media coverage, with many news outlets drawing the obvious comparison to Tatooine, the fictional desert planet from Star Wars that famously orbits two suns. The comparison was apt in a visual sense. Both worlds would see two suns in their skies, though the actual conditions are quite different. Kepler-16b is a cold gas giant, not a habitable desert world. The Tatooine comparison nevertheless helped the public grasp the significance of the discovery, providing a familiar reference point for an otherwise abstract scientific finding. Many people who might not have paid attention to an announcement about transit, photometry, and circumbinary orbital dynamics understood immediately what it meant to find a planet with two suns. The power of science fiction as a cultural touchstone proved valuable. The Discovery team embraced the comparison, even holding a press conference with clips from the film and acknowledging the debt that reality sometimes owes to fiction. The imagination of storytellers had prepared the public to appreciate what astronomers had found. Now the question became, how many more Tatooines were out there waiting to be discovered? The Kepler mission would go on to find additional circumbinary planets in the years following this initial discovery, building a small catalogue of worlds orbiting stellar pairs. Kepler-34b and Kepler-35b were announced in 2012, followed by others with various properties and orbital configurations. Each discovery added to our understanding of how common such worlds might be. Statistical analysis of the Kepler data suggested that circumbinary planets are not particularly rare, with perhaps a few % of close binary star systems hosting detectable planets. Given the billions of binary stars in our galaxy, this implies millions of worlds with double sunsets scattered across the Milky Way. Kepler-16b was just the first we happened to find. The limitations of the transit method mean many circumbinary planets remain undetected, their orbits not aligned in ways that cause them to cross the faces of their stars from our perspective. For every planet we find by transit, many more exist at different orbital angles, invisible to this technique. The true population of circumbinary worlds is certainly larger than our current catalogue suggests. The Kepler Space Telescope itself ended its primary mission in 2013, when the second of its 4 reaction wheels failed, preventing the precise pointing needed for continued observations of its original field. A modified mission called K2 continued until 2018, observing different portions of the sky with reduced but still remarkable precision. The spacecraft was finally retired when it ran out of fuel. The legacy of Kepler lives on in the planets it discovered. Over 2,700 confirmed worlds orbiting stars throughout its field of view. Among these thousands, Kepler-16b remains notable as a first, the planet that opened a new category of worlds to exploration. Other telescopes continue the work of finding planets, building on the foundation Kepler established. The TESS mission, launched in 2018, surveys the entire sky for transiting planets, though its focus on brighter, closer stars makes circumbinary detections more challenging. Future missions may return to systematic searches for planets around binary stars, perhaps finding worlds more suitable for the comparisons to Tatooine that the public finds so compelling. The scientific papers about Kepler-16b have been cited hundreds of times, their findings incorporated into the broader understanding of how planetary systems form and evolve. Theorists have developed new models to explain how planets can form in circumbinary disks, and observers have refined techniques for detecting and characterizing such worlds. The discovery catalyzed an entire subfield of research. The human story of the discovery involves dozens of scientists who contributed to the detection, confirmation, and analysis of the planet. Their names appear on the papers, their work recorded in the scientific literature, their contribution to human knowledge permanent. The planet existed for billions of years before they found it, but their work is what brought it to our awareness. Tonight, as you listen to these words, Kepler-16b continues its orbit just as it did before discovery, just as it will for billions of years after all of us are gone. The planet does not know or care that it has been found, that its existence has been announced and celebrated. It simply orbits, following the laws of gravity as it has since its formation. The discovery of Kepler-16b represents one small step in the larger human project of understanding our place in the cosmos, one data point among many that collectively reshape our view of reality. Each new planet found is a puzzle piece that fits into an ever-growing picture of a galaxy rich with worlds beyond imagining. The picture is far from complete. In the moments ahead, we will explore the mechanics of the planet's orbit in greater detail, understanding how a world can circle two suns and maintain a stable path through the centuries. The orbital mechanics of a planet circling two stars are more complex than the familiar ellipses we learn about in basic astronomy. The simple curves that describe planets orbiting single stars like our Sun. When two stars orbit each other, while a planet orbits both, the gravitational environment becomes dynamic, the center of attraction itself moving as the stars swing around their common center of mass. The planet must navigate this changing landscape. Kepler-16b orbits what astronomers call the barycenter of the binary system, the center of mass around which both stars revolve. This point lies in empty space between the two stars, closer to the more massive orange primary than to the smaller red secondary. The planet traces a path around this mathematical point, rather than around either star individually. The barycenter itself is not stationary from the planet's perspective because the two stars are constantly orbiting it. First, one star on one side, then on the other. From the planet's point of view, the gravitational center of the system appears to wobble, though in reality, it is the planet's perspective that moves relative to the stars. The result is an orbit that is not quite a simple ellipse. Despite this complexity, the orbit of Kepler-16b is remarkably stable, having persisted for billions of years and showing no signs of degradation or chaos. The planet has found a configuration that works, a path through the gravitational landscape that repeats reliably orbit after orbit. This stability was not guaranteed and required specific conditions to achieve. The key to stability is distance. The planet orbits far enough from the stellar pair that it experiences their average gravitational influence rather than being whipsawed by their individual pulls. At roughly 3/4 of an astronomical unit from the barycenter, Kepler-16b is outside the zone where the binary's changing configuration would create destructive tidal forces. It orbits the system as if it were circling a single star. Closer in, where the gravitational environment changes rapidly as the stars orbit each other, stable orbits are impossible. Any planet that formed or wandered too close to the stellar pair would be quickly ejected from the system or sent crashing into one of the stars. The inner region of the system is a no-planet zone, cleared out by gravitational instability. The period of the planet's orbit is 229 Earth days, meaning it takes that long to complete one full circuit around both stars. This is the planet's year, though the concept becomes more complex when your calendar must account for two suns with their own 41-day orbital period around each other. The relationship between these two periods creates patterns that repeat over longer timescales. Every 41 days, the two stars complete one orbit around their common center of mass, returning to the same configuration relative to each other. Every 229 days, the planet completes one orbit around the system. The ratio of these periods means the planet sees roughly 5.5 stellar orbits during each of its own orbits, creating a complex pattern of conjunctions and alignments. The positions of the stars relative to the planet change constantly, with the geometric relationship between planet, orange star, and red star cycling through endless variations. Sometimes the planet is closest to the orange primary, sometimes closest to the red secondary, sometimes roughly equidistant from both. Each configuration creates its own pattern of illumination and temperature. The orbital path of Kepler-16b is slightly elliptical rather than perfectly circular, with an eccentricity of about 0.07. This means the planet's distance from the barycenter varies by about 14% between its closest approach and its farthest point. However, this variation is small compared to the changes in distance to each individual star created by their 41-day orbit. At any given moment, the planet might be closer to one star or the other, but this relationship changes as the stars continue their orbit around each other. The total illumination the planet receives depends on its distances to both stars and their individual luminosities. This creates a complicated pattern of light variation that would make seasons on any moon quite unpredictable by Earth standards. The orbit is also slightly inclined relative to the plane of the stellar orbit, tilted by about half a degree. This small inclination is what allows the planet to transit across the faces of both stars as seen from Earth, the geometric alignment that made detection possible. If the inclination were significantly larger, the planet might never pass in front of either star from our viewing angle. The transit events themselves are complex, occurring in a pattern that reflects the combined orbital motions of planet and stars. Sometimes the planet transits the orange primary, blocking a portion of its brighter light and creating a deeper dip in the combined brightness. Sometimes it transits the red secondary, creating a shallower dip because that star contributes less to the total light. The timing of these transits varies from orbit to orbit because the stars themselves have moved in the time it takes the planet to complete one circuit. The planet might transit one star early in its orbit and the other late, or vice versa, depending on where the stars are in their 41-day dance. Predicting the exact timing requires tracking all three bodies simultaneously. This complexity is what made the discovery both challenging and definitive. The pattern of transits was too intricate to be produced by any simple system, and the only model that fit the observations was a planet in a circumbinary orbit. The complexity itself served as a kind of fingerprint, uniquely identifying the configuration. Gravitational perturbations between the planet and the stellar pair caused small variations in transit timing that provided additional information about the system. The planet's gravity tugs on the stars, slightly altering their orbital timing in ways that depend on the planet's mass. By measuring these tiny variations, astronomers could determine the planet's mass with unusual precision for an exoplanet detected via the transit method. Kepler-16b weighs approximately 1/3 the mass of Jupiter, comparable to Saturn in our own solar system, a substantial world held securely in its complex orbit. The mass confirmed that this was indeed a planet, not some other type of object creating the observed dimming pattern. The stability of this orbit over billions of years required careful arrangement during the system's formation, conditions that astronomers once thought might be too restrictive for planets to meet. The fact that Kepler-16b exists at all demonstrates that nature found a way, that the gravitational complexity of binary systems does not necessarily preclude planet formation. The universe is more accommodating than pessimistic theories suggested. Computer simulations of circumbinary planetary systems show that stable orbits exist only beyond a certain minimum distance from the stellar pair, a boundary called the critical radius. Inside this radius, gravitational perturbations from the orbiting stars would destabilize any planetary orbit within a relatively short astronomical timescale. Outside this radius, planets can survive indefinitely. Kepler-16b orbits just outside this critical radius, close enough to receive meaningful warmth from its two suns, but far enough to maintain long-term stability. This positioning may not be coincidental. Planets that formed closer in would have been ejected or destroyed, leaving only those at safer distances to be discovered. The planet we observe is a survivor. The formation of planets in binary systems remains an active area of research, with models suggesting several possible pathways that could produce worlds like Kepler-16b. The planet may have formed in place from the circumbinary disk of gas and dust that surrounded both stars early in their history. Alternatively, it may have formed farther out and migrated inward. Circumbinary disks are known to exist around young binary stars, rings of material left over from the star formation process that contain the raw ingredients for planet building. These disks are more complex than their single-star counterparts, with the stellar pair carving out an inner cavity and creating density waves that could help or hinder planet formation. The details depend on the specific properties of each system. In the case of Kepler-16, the binary stars are close enough together that they would have shared a common circumbinary disk during their youth, a ring of gas and dust encircling both stars. Within this disk, dust grains would have collided and stuck together, gradually building larger and larger objects over millions of years. Eventually, planetary embryos massive enough to gravitationally attract gas from the disk would have formed. The planet we see today is the end result of this process, a gas giant that accumulated its hydrogen and helium envelope from the ancient disk before that disk dispersed. The process took perhaps 10 million years, a blink of an eye compared to the billions of years the system has existed since. All the complexity of its current orbit was established during that early formative period. The orbital motion of Kepler-16b carries it through a constantly changing gravitational and illumination environment, yet the planet itself likely shows little response to these variations. As a gas giant with no solid surface, the planet has no geography to be heated or cooled by changing stellar distances. Its deep atmosphere responds sluggishly to external changes. The atmospheric circulation patterns on Kepler-16b probably bear some resemblance to those on Saturn in our own solar system, with banded cloud structures and perhaps occasional storm systems. However, the varying illumination from two stars might create subtle differences in atmospheric dynamics that would be fascinating to study with sufficiently powerful instruments. Such observations remain beyond current capabilities. What the planet experiences most directly from its complex orbit is changing total illumination, the combined light from both stars rising and falling as distances vary. During portions of its orbit when it is closer to both stars and the stars are positioned to illuminate the same hemisphere, the planet receives maximum light. When it is farther from both, or when one star is behind the other, it receives less. These variations in illumination would be more noticeable on any moons orbiting the planet than on the gas giant itself, as solid surfaces respond more quickly to changes in incoming radiation. A hypothetical observer on such a moon would experience a year unlike anything possible in a single star system, with brightness fluctuating in complex patterns. The concept of seasons would need to be entirely reconsidered. The orbit of Kepler-16b is also slowly evolving over very long timescales, precessing gradually due to gravitational interactions with the stellar pair. The orientation of the orbit in space shifts over thousands of years, though the basic orbital parameters remain stable. This precession is a normal feature of orbits in multi-body gravitational systems. The discovery of this stable circumbinary orbit overturned decades of theoretical skepticism about whether such configurations could exist in nature. Many astronomers had assumed that the gravitational perturbations in binary systems would be too severe for planets to form or survive. Kepler-16b proved that assumption wrong. The planet's orbit demonstrates that the universe is capable of arrangements that seem improbable from a simple theoretical perspective, that nature explores configurations we might not predict. This lesson has been repeated many times in the history of exoplanet science, as discovery after discovery has revealed worlds that challenged prior expectations. Kepler-16b was one of the most dramatic examples. The 41-day dance of the two stars continues whether anyone observes it or not, a gravitational ballet that has been performed billions of times already. The planet weaves its path around both, tracing an orbit that is complex in detail but stable in essence, a solution to gravitational equations that nature found and has maintained. The choreography continues. For the planet, there is no experience of complexity, no awareness of the mathematical intricacy of its path through space and time. There is only the endless circling, the constant pull of gravity, the slow progression through configurations that repeat and vary in patterns too long for any mind to directly perceive. The orbit simply is, as it has been for ages. The light that reaches Kepler-16b comes from two sources that move independently across its sky, creating illumination patterns unlike anything possible on a world orbiting a single star. Every moment of every day, the planet receives photons from both the orange primary and the red secondary, their light mixing in proportions that change as the stars orbit each other. The result is a visual environment of extraordinary complexity. On Earth, shadows are simple. A single light source creates a single shadow for each object, and that shadow has the complementary color of the light. On Kepler-16b, or on any moon that might orbit it, objects would cast two shadows, one from each sun, slightly offset from each other and tinted differently. The overlap and separation of these shadows would shift constantly. When both suns are high in the sky and separated by a significant angle, each object would cast two distinct shadows, pointing in different directions. The shadow cast by the orange star would be tinged slightly blue, while the shadow cast by the red star would lean towards cyan, as shadows take on the complementary color of their light source. The ground between these shadows would receive mixed light from both stars. As the suns move through their orbital dance, the angle between them changes, and the shadows respond accordingly. When the suns are close together in the sky, the two shadows would nearly overlap, creating a darker core with lighter penumbral edges where only one star's light is blocked. When the suns are widely separated, the shadows would stretch in opposite directions. The color of ambient light on this world would be warmer than Earth's sunlight, shifted toward the orange and red end of the spectrum by the cooler temperatures of both stars. Neither star is as hot as our yellow sun, and their combined light would create an illumination reminiscent of perpetual late afternoon on Earth. Shadows would be softer and warmer. The total brightness reaching the planet varies as the geometric relationship between planet and stars changes throughout the complex overlapping orbital periods. At some points in its orbit, Kepler-16b receives nearly as much total light as Earth receives from the Sun. At other points, the light drops significantly, creating variations that would be noticeable to any observer. The orange primary star, Kepler-16a, provides the majority of the system's light, contributing roughly 3/4 of the total illumination when both stars are visible. The red secondary, Kepler-16b, adds its own contribution, perhaps 1/4 of the total, but in a distinctly different color. The mixing of these two light sources creates the unique visual character of this system. When the red star passes behind the orange star from the planet's perspective, the total light drops as only the orange sun remains visible. These eclipses occur regularly as part of the star's 41-day orbital period, predictable events that would mark time for any observer on or near the planet. The sky would subtly shift in color during these events. Similarly, when the orange star passes behind the red star, the illumination changes more dramatically because the primary light source is temporarily blocked. The world would dim noticeably, lit only by the fainter red sun until the primary emerges from behind its companion. These mutual eclipses add another layer to the complex light environment. The visual experience of this world, imagined from the perspective of a hypothetical observer, would be one of constant subtle change, a light environment that never quite repeats exactly the same way twice within any human-length timescale. The two suns rise at different rates, set at different times, and follow paths that interweave in patterns dictated by orbital mechanics. If you could stand on a moon of Kepler-16b and watch the sky over the course of the planet's 229-day year, you would see the two suns complete their 41-day dance around each other roughly 5.5 times. Each stellar orbit would bring the suns into different positions relative to the horizon, creating sunrise and sunset combinations that vary from orbit to orbit. Sometimes both suns would rise together, their disks nearly touching as they climb above the horizon in tandem, flooding the landscape with their combined warm light. Hours later, they might set separately, the smaller red sun dipping below the horizon, while the orange sun lingers for another hour or more. The timing depends on the exact phase of the stellar orbit. Other times, one sun might rise while the other is already high in the sky, having risen earlier in what passes for night on this strange world. The concept of night itself becomes complicated when one sun might set only to have the other still shining, creating twilight conditions that persist until the second sun also sets. True darkness would require both suns below the horizon. The shadows cast by objects on the surface of a hypothetical moon would tell time in a way far more complex than any sundial on Earth could manage. The two shadows would move at different rates, their angles and lengths encoding information about the positions of both suns in the sky. An observer could learn to read these shadow patterns. When both shadows point in similar directions, both suns are roughly aligned in the sky, either both high or both low on the same side of the horizon. When the shadows point in opposite directions, the suns are on opposite sides of the sky, creating illumination from multiple angles that fills in shadows from each direction. The interplay is endless. The color of the sky itself might shift depending on atmospheric composition and the angle of incoming light, though we can only speculate about what atmosphere a moon of Kepler-16b might possess. If it had a thick nitrogen atmosphere like Earth's, the sky might take on hues influenced by the orange and red light being scattered, perhaps producing sunset-like colors even at midday. The psychological effect of living under such a sky would be profound, though entirely hypothetical since no life is known to exist in this system. The constant interplay of two light sources, the shifting shadows, the varying colors, all would create a sensory environment utterly unlike anything any Earth creature has ever experienced. The strangeness would be beautiful. Even without observers, the light from two suns plays across the cloud tops of Kepler-16b, illuminating atmospheric features in ways that differ from anything in our solar system. The banded clouds of this Saturn-sized world catch light from two directions simultaneously, creating visual effects that no spacecraft has ever photographed. We can only imagine. The Terminator line between day and night on the planet would be more complex than on a single sun world, with the positions of both stars determining exactly where night falls at any moment. The Terminator might be curved or irregular, shaped by the geometry of illumination from two sources at different positions. Twilight zones would be especially complex. As the planet rotates on its axis, a rotation period we have not yet measured, different parts of its cloud-covered surface sweep through zones of double illumination, single illumination from either star, and darkness when both suns are below the local horizon. The daily experience of any point on the planet involves this cycling through light conditions. The beauty of this double illumination exists whether or not anyone ever observes it directly. Photons streaming across 3/4 of an astronomical unit to splash against hydrogen and helium clouds that absorb and reflect according to the laws of physics. The light simply does what light does, painting a world in colors that human eyes have never seen. The concept of seasons becomes remarkably complex on a world that orbits two stars rather than one, with variations in light and temperature driven by multiple interacting cycles rather than a single annual pattern. On Earth, seasons arise from the tilt of our planet's axis, which causes different hemispheres to lean toward or away from the sun throughout the year. Kepler-16b adds layers of complexity. The planet's axial tilt, if it has one, would create some seasonal variation as different hemispheres receive more direct illumination at different points in the orbit, similar to the basic mechanism on Earth. However, this effect would be superimposed on other variations caused by the changing distance to each star and the changing relative positions of the two stars. The result defies simple description. The 229-day orbital period of Kepler-16b determines the longest cycle of variation, the planetary year during which the world completes one full circuit around both stars. During this period, the distance between the planet and the barycenter of the stellar system varies somewhat, but more importantly, the planet's distance to each individual star changes dramatically. At some points in its orbit, the planet finds itself closer to the orange primary star, while the red secondary is on the far side of the system. At other points, the geometry reverses, placing the planet nearer to the smaller red star, while the orange star recedes. The total warmth received depends on the combined effect of distances to both stars weighted by their different luminosities. The 41-day orbital period of the two stars around each other creates a shorter cycle of variation that occurs roughly 5.5 times per planetary year. During each stellar orbit, the two suns move through their dance, sometimes aligning to present maximum combined illumination, sometimes arranging themselves so one partially or fully eclipses the other. These stellar eclipses reduce the total light reaching the planet for their duration, which lasts a few hours each time they occur. While a single eclipse would have minimal effect on planetary temperature, the cumulative effect of regular eclipses throughout the year might create a subtle modulation in the thermal budget. The planet's atmosphere would smooth out short-term variations. The relationship between the planetary orbital period and the stellar orbital period creates longer patterns that emerge from the interaction of these two fundamental cycles. Over the course of many planetary years, the relative timing of planet position and stellar configuration varies, creating what might be called superseasons or metacycles of illumination. These patterns would repeat only over timescales much longer than a single orbit. For any hypothetical observer trying to predict the weather or illumination conditions, the complexity would be daunting compared to the simple seasonal patterns we experience on Earth. Almanacs would need to track both the position of the planet in its orbit and the current phase of the stellar orbit, combining these to predict upcoming light conditions. Temperature variations on the planet itself are probably minimal despite the complex illumination patterns, because gas giants have deep atmospheres that store enormous amounts of thermal energy. The sluggish response of a hydrogen-helium atmosphere to changes in incoming radiation means that short-term variations smooth out, leaving only the longest-term trends to influence conditions. The planet maintains a relatively constant temperature. That temperature is cold by Earth standards, estimated at roughly -70 to -100 degrees Celsius, based on the total radiation the planet receives, and reasonable assumptions about its atmospheric properties. This places Kepler-16b in a frigid realm, colder than any natural environment on Earth, a frozen giant drifting through the outer reaches of its binary system. The coldness arises from the dimness of both stars and the planet's distance from them. Despite receiving light from two suns, the total illumination amounts to less than Earth receives from our single sun, because both stars are cooler and the planet orbits farther out than Earth does. The romance of two suns in the sky does not translate to tropical warmth. If moons orbit Kepler-16b, they would experience much more noticeable variations in illumination than the planet itself, lacking the thermal inertia of a deep gas giant atmosphere. A rocky or icy moon with a thin atmosphere would heat and cool relatively quickly as light conditions changed, experiencing something like weather driven by the stellar cycles. On such a hypothetical moon, a day might begin with one sun rising, bathing the landscape in orange light that warms the surface after the cold of night when both suns were down. Hours later, the second sun rises, adding its redder light to the mix and boosting the total illumination significantly. The temperature continues to climb as both suns ride higher. Later, one sun might set while the other remains high, beginning a transition to lower illumination, but not yet full darkness. The single sun provides enough light to see by, and enough warmth to moderate the cooling that began when its companion set. The shadows from this single sun would be simpler now, each object casting just one dark shape. Finally, the second sun also sets, and true night falls, with both suns below the horizon and only starlight illuminating the frozen landscape. The temperature drops steadily through this night, reaching its minimum just before the first sun rises again to begin the cycle anew. The pattern of warming and cooling repeats, with variations. But this simple daily cycle would be modulated by the 41-day stellar orbit and the 229-day planetary orbit, creating longer patterns of variation that would make each day slightly different from the last. The height each sun reaches in the sky, the duration each remains visible, the interval of true night, all would vary as the complex orbital mechanics unfold. Understanding seasons on Kepler-16b requires abandoning the simple framework that works for Earth, the four-season pattern driven by axial tilt that gives us spring, summer, autumn, and winter in predictable sequence. Here, seasons would be multi-dimensional, with different cycles operating simultaneously and combining in ways that resist simple categorization. Perhaps the most meaningful definition of a year on this world would be the full 229-day orbital period, the time required for the planet to return to the same position relative to its binary stars. But even this definition is imperfect. because the stars themselves have continued their dance during that time, and the exact alignment of all three bodies never quite repeats exactly. Over very long timescales, the precession of the planet's orbit would create even longer cycles, slowly changing the relationship between the orbit and any axial tilt the planet might have. These cycles would operate over thousands of years, far too long for any observer to directly experience, but potentially detectable through patient astronomical observation. The complexity is beautiful in its mathematical richness, a three-body gravitational dance that produces patterns within patterns, cycles within cycles. The planet and its two suns move through their choreography following laws that Newton first described, creating a light show that has played out for billions of years. The seasons change, though not in ways we intuitively understand. Gas giants in our own solar system are accompanied by extensive families of moons, ranging from tiny, irregular rocks to worlds larger than some planets. And there is every reason to suspect that Kepler-16b hosts its own collection of natural satellites. Jupiter has at least 95 known moons. Saturn has over 140, and these numbers continue to grow as our detection capabilities improve. A Saturn-sized planet around two stars could easily possess dozens of moons. The largest moons of our gas giants are remarkable worlds in their own right, with Titan hosting a thick atmosphere and liquid methane lakes, Europa hiding a subsurface ocean beneath an icy crust, and Ganymede exceeding Mercury in size while possessing its own magnetic field. Moons around Kepler-16b could be equally diverse and fascinating. Detecting moons around exoplanets remains extremely difficult with current technology, as the signals they produce are far smaller than those of the planets themselves. No moon has been conclusively confirmed around any exoplanet as of yet, though candidate signals have been identified in some systems. Kepler-16b's moons, if they exist, remain invisible to our instruments. The gravitational environment around a circumbinary planet adds complexity to the question of moon stability, as the varying gravitational field from the two stars could potentially destabilize lunar orbits over long timescales. However, moons orbiting close to their parent planet should be protected from these effects, experiencing primarily the planet's gravity rather than the more distant stellar influence. If we imagine moons orbiting Kepler-16b, we can speculate about what conditions they might experience based on what we know about the system and about moons in general. A moon the size of Titan, orbiting a few 100,000 kilometers from the planet, would be close enough to be gravitationally bound securely, while far enough to avoid rapid orbital decay. Such a moon would share its parent planet's view of two suns, experiencing the same complex illumination patterns we have described, but with the added complication of the planet itself sometimes blocking one or both suns from view. Eclipses by the planet would be regular events, plunging the moon into the giant world's shadow for hours at a time as it orbited around. The temperature on such a moon would depend critically on whether it possessed any atmosphere and on whether tidal heating from the planet's gravity provided any internal warmth. In our solar system, tidal heating keeps Europa's subsurface ocean liquid and drives the volcanic activity on Io. Similar effects could operate on moons of Kepler-16b. A tidally heated moon might maintain liquid water beneath an icy crust, despite the cold temperatures of the outer circumbinary region, creating a potential habitat for life in an unlikely location. The energy from gravitational flexing as the moon orbits its planet could substitute for the stellar warmth that such a distant world lacks. The possibility is tantalizing. The surface of a hypothetical moon orbiting Kepler-16b would experience a visual environment of extraordinary complexity, with the planet itself dominating a significant portion of the sky, depending on the moon's orbital distance. A close orbiting moon might see the gas giant spanning dozens of degrees, a massive presence that waxes and wanes as the moon circles around. The planet would reflect light from both suns, appearing as a bright object in the moon's sky when fully illuminated, perhaps bright enough to cast shadows of its own. The reflected light would carry the mixed orange and red hues of the binary stars, creating a warm glow that might provide some illumination even during the moon's night when both suns are below the horizon. The phases of the planet as seen from the moon would follow the lunar orbit, with the giant world appearing full when the moon is between the planet and the suns, and appearing as a thin crescent when the moon is on the sunward side. The phase cycle would repeat with each lunar orbit, perhaps every few days or weeks depending on the orbital parameters. During eclipses, when the moon passes through the planet's shadow, both suns would be blocked simultaneously by the looming bulk of Kepler-16b. These events would bring true darkness, the deepest nights the moon could experience, with temperatures dropping rapidly as all sources of external heat vanished temporarily. The surface would grow cold and still. The view from such a moon would be among the most spectacular in the known universe. A landscape of alien geology illuminated by two suns and dominated by a giant planet whose cloud bands might be visible to the naked eye. The colors would be unlike anything on Earth, warmer and redder with double shadows and complex lighting. The beauty would be profound. If the moon possessed an atmosphere, that atmosphere might produce its own colors and phenomena, perhaps hazes that scattered the orange and red light into sunset-like skies even at midday. Clouds might form from exotic materials depending on the temperature and composition. Perhaps water, ice at the temperatures prevailing in this cold system. Perhaps something more unusual. The potential for liquid water, either on the surface under special conditions or beneath an icy crust maintained by tidal heating, raises the possibility that such a moon could be habitable in some limited sense. Life as we know it requires liquid water, energy, and organic chemistry, and all three might be present on the right kind of moon around Kepler-16b. This is speculation built on speculation, possibilities stacked on possibilities, but it is grounded in what we know about moons in our own solar system and what we understand about planetary physics. The moons of Kepler-16b, if they exist, are real places with real properties waiting to be discovered. We simply lack the ability to see them yet. The formation of moons around a circumbinary planet could have followed several pathways, similar to how moons form around planets in single star systems. Some moons may have formed in place from a disk of material surrounding the young planet, condensing from gas and dust in the same way the planet itself formed from the circumbinary disk. Other moons might be captured objects, asteroids, or other small bodies that wandered too close to the planet and became gravitationally bound through interactions that shed enough energy to prevent escape. The irregular moons of Jupiter and Saturn, with their chaotic orbits and varied compositions, likely formed through such capture processes. The largest moons, if Kepler-16b possesses any, comparable to Titan or Ganymede, probably formed in place from a circumplanetary disk, growing massive enough to gravitationally attract and retain their own atmospheres. Such moons would be small worlds in their own right, with complex geology and potentially active surfaces shaped by internal heat. Whatever moons orbit Kepler-16b, they have been there for billions of years. evolving alongside the planet and the binary stars in the complex gravitational environment of this system. They have witnessed countless stellar orbits, countless planetary years, countless cycles of the complex dance we have described. They persist, unseen, but almost certainly present. The discovery of Kepler-16b in 2011 opened a new category of worlds to scientific investigation, proving that circumbinary planets exist and inspiring searches that would find many more examples in the years that followed. This was not merely the discovery of one unusual world, but the revelation of an entire population of planets that orbit binary stars throughout the galaxy. Before Kepler-16b, the existence of such planets was debated, with theoretical arguments both for and against their formation and survival in the complex gravitational environments of binary star systems. The discovery resolved this debate decisively. Nature had found a way, and the task now was to understand how common these worlds might be and what properties they possessed. Within a few years of the first discovery, the Kepler mission had identified several more circumbinary planets, each with its own unique characteristics determined by the properties of its stellar hosts and its orbital parameters. Kepler-34b and Kepler-35b were announced in 2012, two more gas giants orbiting binary stars in the same general region of sky. Kepler-34b orbits a pair of sun-like stars, both similar in temperature and brightness to our own star, creating a double illumination that would appear more yellow-white than the orange-red of Kepler-16b. The planet completes an orbit every 289 days, slightly longer than its famous predecessor. Both stars contribute significant light. Kepler-35b orbits a somewhat different binary, with one star similar to our Sun and the other a smaller, cooler companion. The planet's orbit takes 131 days, shorter than Kepler-16b, placing it in a somewhat warmer region of its system. Each circumbinary planet tells its own story about the diversity possible in these systems. The count of confirmed circumbinary planets has grown steadily since those early discoveries, with more than a dozen now known and additional candidates awaiting confirmation through follow-up observations. Each new discovery adds to our understanding of how these systems form and what range of configurations can remain stable over astronomical timescales. Kepler-47 is a particularly interesting system, hosting multiple planets orbiting the same binary star pair. At least 3 planets have been confirmed in this system, demonstrating that circumbinary planetary systems can be as complex as those around single stars. The planets orbit at different distances, with the innermost completing its orbit in roughly 50 days. The outermost known planet in the Kepler-47 system orbits in what astronomers call the habitable zone, the region where temperatures might allow liquid water to exist on a planetary surface. This planet is a gas giant, unlikely to host life itself, but any large moons it possesses might experience conditions compatible with liquid water. The possibility is intriguing. Kepler-453b represents another milestone, a circumbinary planet in the habitable zone of its binary star system. Discovered in 2015, this world orbits 2 stars, one similar to our Sun and one smaller, at a distance that places it in the temperature range where water could remain liquid. The planet is about 6 times Earth's mass. The diversity of circumbinary planets discovered so far suggests that such worlds are not rare accidents, but a natural outcome of planet formation processes that can operate in binary systems as well as around single stars. The galaxy likely contains millions of circumbinary planets, most of them too far away or too faint for current instruments to detect. Some of these undiscovered worlds may be rocky planets rather than gas giants, small worlds with solid surfaces where an observer could actually stand and watch two suns cross the sky. The known circumbinary planets are mostly gas giants because these are easier to detect. But smaller worlds almost certainly exist in these systems as well. The techniques used to find circumbinary planets continue to improve, with newer missions and more sensitive instruments pushing the boundaries of what can be detected from Earth or from space-based observatories. The Transiting Exoplanet Survey Satellite, or TESS, has searched much of the sky and identified circumbinary planet candidates that await confirmation. Future telescopes will push these boundaries further still, potentially detecting Earth-sized circumbinary planets in the habitable zones of their binary stars. Such a discovery would raise profound questions about the potential for life on worlds with two suns, environments so different from Earth that biological evolution might produce utterly alien results. The formation of circumbinary planets requires conditions in the protoplanetary disk that allow material to accumulate despite the gravitational perturbations from two central stars. The inner regions of such disks are strongly disturbed, with the binary's gravity creating spiral waves and clearing out material close to the stars. Planets must form in the calmer outer regions. Once formed, planets in circumbinary systems may migrate inward, drifting through the disk until they reach the inner stability boundary, where closer approach would be dynamically forbidden. Many known circumbinary planets orbit near this boundary, suggesting that migration played a role in placing them in their current locations. The migration process itself is influenced by the binary stars, with the time-varying gravitational field creating conditions different from those around single stars. Understanding these differences requires sophisticated computer simulations that model the complex interactions between forming planets and the binary disturbed disk. The field is still developing. What emerges from these studies is a picture of circumbinary planet formation as challenging but not impossible, requiring specific conditions but not impossibly rare ones. The discovery of multiple circumbinary planets in the Kepler field suggests that perhaps 10% of close binary stars may host planets, a substantial fraction of a large population. The existence of planets orbiting two stars has implications beyond planetary science, touching on questions about the history and future of stellar systems throughout the galaxy. Binary stars are common, comprising perhaps half of all star systems, and, if a significant fraction of these host planets, the total number of circumbinary worlds in the Milky Way alone could number in the billions. Some of these worlds may exist in habitable zones, receiving enough warmth from their two stars to maintain liquid water on their surfaces or on the surfaces of moons that orbit them. The search for life beyond Earth naturally extends to these unusual systems, even if the conditions there seem strange by our standards. Life on a circumbinary planet would experience environmental conditions quite different from those on Earth, with variations in illumination and perhaps temperature that follow complex patterns rather than simple seasonal cycles. Evolution would shape organisms to cope with these conditions, potentially producing biological solutions we cannot imagine from our single-star perspective. The science fiction vision of worlds with two suns, popularized by countless stories and films, has proven to be scientifically valid, grounded in astronomical reality rather than pure imagination. Kepler-16b and its cousins are real places, actual worlds orbiting actual binary stars, waiting for future generations to study them in greater detail. The distance separating Earth from Kepler-16b spans 245 light-years, a gulf of space so vast that the numbers used to describe it lose meaning for minds evolved to navigate distances measured in footsteps and horizons. A light-year is the distance light travels in 1 year, roughly 9.5 trillion kilometers, and we must multiply that by 245 to reach this world with 2 suns. At the speed of a modern spacecraft, perhaps 40,000 kilometers per hour, the journey would take approximately 7 million years, longer than humans have existed as a species on Earth. Generations beyond counting would live and die aboard any vessel attempting such a crossing, their descendants losing all memory of the departure point or the purpose of the voyage. Even light, the fastest thing in the universe, requires 245 years to cross the distance between that binary star system and our own solar system. The photons that the Kepler Space Telescope detected when confirming this planet's existence began their journey before the American Revolution, before the steam engine was invented, before most of modern history unfolded on our distant world. The light arriving at Earth tonight from Kepler-16 shows us the system as it existed around the year 1780, when the United States was newly independent and the French Revolution had not yet begun. Whatever is happening there now, if the planet still orbits, if the stars still shine, we will not know about it until the year 2270 or so. This delay between reality and observation is one of the fundamental limitations of astronomy, a field built entirely on ancient light that carries news of the past rather than the present. We never see the universe as it currently is, only as it was when the light we observe began its long journey across the darkness between stars. The farther we look, the deeper into history we see. For Kepler-16b, the 245-year delay is short by astronomical standards, a mere eye blink compared to the light travel times from distant galaxies, or even from stars on the far side of our own Milky Way. The system is relatively nearby, a close neighbor in the vast suburbs of the galaxy that contains us both. The constellation Cygnus, where Kepler-16 appears from our perspective, is visible in the northern sky during summer and autumn months. Its distinctive cross shape marking a region rich with stars and nebulae along the plane of the Milky Way. Ancient cultures saw a swan or a cross in these stars, never imagining the worlds that orbit suns too faint for human eyes to detect. If you know where to look on a dark night, you can point toward the region of sky where this binary star system continues its ancient operations, invisible but present. Too dim to see, but not too dim to influence our understanding of what the universe contains. The planet orbits there, whether anyone on Earth observes it or not. The inability to visit Kepler-16b, to send probes or astronauts across the 245 light-years that separate us, means that everything we know about this world comes from light alone. We catch photons that began their journey centuries ago and decode the information they carry about their source, piecing together a picture of a world we can never directly touch. This indirect way of knowing defines all of astronomy beyond our immediate solar system, where spacecraft can still visit and return data within human timescales. For exoplanets like Kepler-16b, we must content ourselves with what light can tell us. Sizes, orbits, masses, and sometimes atmospheric compositions, while the direct experience of these worlds remains forever beyond reach. There is something both limiting and liberating about this constraint, a boundary that keeps us humble about what we can truly know while freeing us to imagine what we cannot directly observe. The double sunsets of Kepler-16b exist in our models and our minds, constructed from data but experienced only through imagination. The wonder is real even if the direct experience is impossible. Future generations may develop technologies that make interstellar distances less absolute, methods of propulsion that could carry probes across light years within centuries rather than millions of years. Such technologies remain speculative, existing in theory and science fiction, but not in any engineering reality we can currently build. The distance remains, for now, effectively infinite. The Kepler Space Telescope, which discovered this planet and over 2,000 others during its operational lifetime, orbited the Sun in a path that slowly drifted away from Earth, an independent journey through space that eventually carried it beyond easy communication range. The telescope was retired in 2018 after its reaction wheels failed and its fuel was exhausted. During its mission, Kepler stared at a single patch of sky in the constellation Cygnus, monitoring the brightness of over 150,000 stars simultaneously, watching for the tiny dips in light that reveal planets passing in front of their host stars. Kepler-16 was one of those stars, and the complex dimming pattern it showed revealed the circumbinary planet that has been our subject tonight. The data Kepler collected continues to yield discoveries years after the telescope itself went silent, as astronomers develop new techniques to extract information from the archived observations. Planets that were initially overlooked are found upon reanalysis, and the properties of known planets are refined through additional study. The mission's legacy continues to grow. Other telescopes have taken up the planet-hunting work that Kepler pioneered, scanning different portions of the sky with improved instruments and techniques. The Transiting Exoplanet Survey satellite surveys nearly the entire sky, while ground-based observatories contribute their own discoveries. The catalogue of known exoplanets grows steadily larger. The patience required for astronomical discovery extends beyond individual observations to the entire arc of scientific progress. Decades and centuries of accumulated effort building toward understanding that no single generation could achieve alone. The astronomers who discovered Kepler-16b built on work stretching back to Galileo and beyond, each generation adding to what the next would know. Future astronomers will build on what we know today, developing instruments and techniques that'll make our current capabilities seem primitive by comparison. They may directly image circumbinary planets, measuring their colors and spectra with precision we cannot currently achieve. They may find biosignatures on circumbinary worlds that hint at life under two suns. This long arc of discovery is one of humanity's most remarkable achievements, the slow accumulation of knowledge about a universe that does not make observation easy. We are not privileged observers with special access to cosmic truths. We are creatures on a small world who have learned to read the faint messages that light carries across unimaginable distances. Kepler-16b is one of those messages, a world revealed through patient observation and careful analysis, a place we know exists because of photons that traveled for 245 years to tell us so. The conversation between humanity and the cosmos continues, one discovery at a time, one world at a time. The stars that appear in tonight's sky, if you can see them, are not where they seem to be, having moved in their orbits around the galactic center since their light began traveling toward Earth. Kepler-16 and its binary companion have drifted slightly since the light we observed departed, though not far enough to leave the constellation Cygnus or significantly change their apparent position. Over millions of years, the slow drift of stars through the galaxy, will rearrange the constellations entirely, erasing the patterns that ancient humans named and creating new arrangements that future observers might name differently. The Swan will fly apart, its stars scattering along their individual orbital paths, though this process is far too slow for any human lifetime to notice. Kepler-16b will continue orbiting its two stars throughout these changes, following its 229-day path around the barycenter as it has for billions of years already. The system is stable and will persist for billions of years more, long after any current human concerns have faded into the remotest history. The distance between us measures more than space. It measures time and change, and the limits of what we can know about places we cannot visit. 245 light-years is a boundary we can observe across but not cross, a separation that makes Kepler-16b forever a world of light and inference, rather than direct experience. The two suns of Kepler-16 continue their 41-day dance around each other tonight, as they have for billions of years and will for billions more, their gravitational embrace neither tightening nor loosening with the passage of ages. The orange primary and its smaller red companion circle their common center of mass with clockwork precision, partners in a waltz that predates the existence of life on Earth. Around this dancing pair, the planet Kepler-16b traces its own patient orbit, completing each circuit in 229 days as it weaves through the complex gravitational landscape of the binary system. The planet has made this journey billions of times already, each orbit nearly identical to the last, each bringing the same complex patterns of illumination from two stars. The double sunsets occur regularly as the planet rotates beneath its twin suns, moments when first one, then the other, or sometimes both together, dip below whatever horizon a gas giant can be said to have. The cloud tops of this Saturn-sized world catch the changing light, reflecting orange and red in proportions that shift as the suns move through their dance. No eyes have ever witnessed these sunsets. No mind has ever contemplated the beauty of two suns sinking into an alien horizon on this distant world. The phenomenon exists nonetheless, photons streaming across space and interacting with hydrogen and helium clouds according to the laws of physics, creating visual effects that require no observer to be real. The light from those two suns falls equally on whatever moons might orbit Kepler-16b, illuminating surfaces that may be rocky or icy, barren or perhaps sheltering liquid water beneath frozen crusts. These hypothetical moons, if they exist, have experienced their own billions of years of circumbinary sunsets, two lights rising and setting in patterns that never quite repeat. On such a moon, an observer would see the planet itself as a dominant presence in the sky, a Saturn-like world banded with clouds and perhaps encircled by rings, if the system possesses them. The planet would wax and wane through phases as the moon orbited around it, sometimes brilliantly lit by both suns, sometimes a thin crescent against the dark. The shadows on such a moon would be double, as we have described, two dark shapes stretching from every rock and ridge, offset from each other and tinted in complementary colors. The shadows would move at different rates as the two suns traced their separate paths across the sky, sometimes converging, sometimes spreading apart, always changing. The cold of this distant region would grip such a moon tightly, with temperatures far below zero and perhaps approaching the limits of what any known chemistry could sustain. Yet, even in such cold, the beauty would be profound, a visual environment of extraordinary richness created by the simple fact of two suns instead of one. The universe contains countless wonders that exist whether or not any observer contemplates them. Phenomena that unfold according to physical law regardless of appreciation or attention. The double sunsets of Kepler-16b are one such wonder, a spectacle that has occurred countless times without witness, beauty that requires no validation to be real. This is perhaps one of the most humbling aspects of astronomy, the recognition that the cosmos is not arranged for our benefit or observation, that it operates on its own terms across timescales and distances that dwarf human concerns. The binary stars and their planet existed for billions of years before we evolved to notice them, and will continue for billions more after we are gone. Our observation changes nothing about that distant world, adds nothing to its sunsets, subtracts nothing from its orbital mechanics. We are witnesses only, looking across 245 light-years of void to glimpse a system that neither knows nor cares that we exist. The light simply travels, and we catch what we can. Yet there is meaning in the observation nonetheless, value in the knowing even when the knowing changes nothing about what is known. We are richer for understanding that worlds with two suns exist, that the science fiction vision has astronomical reality, that the universe contains more diversity than our limited imaginations might have supposed. The thoughts of distant sunsets can accompany you now as wakefulness begins to fade. Images of orange and red light mixing above alien horizons. Double shadows stretching across surfaces we can only imagine. The complexity of circumbinary orbits simplifies into a gentle mental picture, two suns setting while a cold gas giant drifts through its ancient path. The numbers fall away. 245 light-years, 229 days, 41 days, leaving only the images, only the sense of a distant place where something beautiful happens whether anyone watches or not. The facts have served their purpose, carrying you to a moment of contemplation, and now they can rest. Kepler-16b continues its orbit as your thoughts grow quiet, as your breathing slows, as the concerns of the day release their grip on attention that would rather wander among stars. The planet has no awareness of your contemplation, no knowledge that a mind on a distant world has spent an hour considering its strange double sunlight. This mutual unawareness is not lonely but peaceful, a recognition that the universe proceeds on its own terms while we proceed on ours, each spinning through our respective orbits without the burden of cosmic significance. The planet orbits because gravity requires it to. We rest because biology invites it. The stars outside your window, if you can see them, include the region of sky where Kepler-16 shines too dimly for human eyes, a point of light lost among the thousands visible on a dark night. Somewhere in that direction, two suns orbit each other, while a planet orbits both, a system as real as our own, though separated by distances that mock our fastest technologies. The constellations wheel slowly overhead as Earth rotates, carrying you through the night toward dawn, while the stars maintain their apparent positions, faithful companions to every human who has ever looked upward and wondered. The ancient patterns persist, though now we know what lies hidden within them. Worlds beyond counting, many stranger than imagination. Kepler-16b is one of those hidden worlds, a gas giant with two suns that rises and sets in patterns no Earth creature has ever experienced. The discovery of this world expanded our understanding of what is possible, proved that planets can thrive in the gravitational complexity of binary systems, added a new category to the cosmic catalogue. Tonight, that knowledge rests with you as you rest. absorbed into the background understanding of a universe vaster and more varied than any previous generation knew. The double sunsets are real, occurring right now as you listen to these words. Two suns painting clouds with colors we can only imagine. The journey we have shared tonight reaches its end, but the world we explored continues its ancient operations, indifferent to our attention, beautiful without our observation. Two suns rise and set over Kepler-16b, as they have for billions of years, as they will for billions more, patient and perpetual. The light from those suns streams through space at 300,000 kilometers per second, some of it aimed by pure chance toward a small blue planet where curious creatures have built instruments to catch it. That light carries information about temperatures and compositions and orbital mechanics, but it also carries something less measurable: the simple fact that such a world exists. We are fortunate to live in an age when such knowledge is possible, when the technology exists to detect planets orbiting stars so distant that their light takes centuries to reach us. Previous generations could only wonder whether other worlds existed. We know that they do, in numbers too large to fully comprehend. Kepler-16b is one world among billions, one system among countless stellar neighborhoods, scattered throughout a galaxy that is itself one among trillions. The cosmic context is humbling, but within that vastness, each world is real. Each sunset actually occurs. Each photon actually travels the distance to reach us. Rest now, if you are ready, letting the images of two suns settle into the quiet of approaching sleep. The orange and red light plays across your imagination, painting skies that no human will ever directly see, but that exist nonetheless, real and beautiful in their distant corner of the cosmos. The planet continues its orbit while you rest, completing another fraction of its 229-day year as hours pass on Earth. The two stars continue their dance, the 41-day period advancing by minutes and hours as you drift toward dreams. The universe keeps its own time. The darkness beyond your window is the same darkness that fills the space between stars, the void through which light travels for years and centuries to bring news of distant worlds. That darkness is not empty, but full of photons in transit, messages from places like Kepler-16b, making their patient way toward wherever they will eventually arrive. Tomorrow, the universe will still be there, ancient and vast and full of worlds we have not yet discovered, double sunsets we have not yet imagined. The curiosity that brought you here tonight will return when it is ready, and there will always be more to explore, more to wonder about, more to carry you through quiet hours. The two suns set once more over an alien world, their light mingling into twilight colors that no human eye has witnessed. And somewhere in the constellation Cygnus, a planet continues its patient orbit around stars that have danced together for billions of years. Good night from the drowsy astronaut. Sleep well, and we'll explore the cosmos together again soon.